Hey all, welcome back to another round of Robinson Rants. And yeah, let's get going. First off, I should take a moment and just warn you, we're going to go through and do a couple sets of example problems using RLC circuits. And at the very end of the video, I'll probably point out to you, hey, here's a chart and, here's how you can kind of skip some of this mathy stuff if you need to. But you really should understand the math before you actually start using the chart. So that's one warning. The second warning is always make sure your microphone's on. Okay. So let's go ahead and get started with these problems. And I'll probably work in terms of variables, at least for maybe the first or the second one, just so that we can kind of see how everything works. And then maybe after that, I'll probably just do numbers instead. So you can see it both ways. Okay, well, let's go at it. So what we have here is a circuit containing, of course, a capacitor and inductor and some resistors. And we're going to flip the switch from A to B at times equals 0. And what we're asked to find is V naught of t. In other words, the drop, the potential drop across the capacitor. So as you've probably noticed for each of these problems, you're really solving two problems. One of them is what happens before the switch is thrown, the initial conditions, and then we have to go and do what happens after the switch is thrown. Okay, so the final state. And then we have to use that at time equals 0, that connection point between the initial and final states to get everything to match up. Okay? So I guess this goes along with my first comment, is that you can, yes, write down a chart. Here's the solution if this happens. Here's the solution if this happens. Here's the solution if this happens. And those solutions are perfectly general. Okay? How you make them specific to the circuit you're given is by those initial conditions. Okay? Cool. So let's go at it. So first of all, we have our initial state. And in that, you can completely ignore that resistor. It's as if that resistor is not even there. And furthermore, during our initial state, we can assume that L's and C's are fully charged. And what does that mean in terms of their behavior in the circuit? Yeah, that the L's, the inductor, acts like a perfect wire, and the capacitor acts like a brake. Okay. So we can even remove this guy. It's as if that's not there. And so what we have is, I'll call this V1. We have our V1 supply. We have R1. We'll go through. We have R2, that 480 ohm. We have our inductor, and then we have a second potential supply. Call that V2. So this is the circuit that we're asked to analyze for our initial state. Well, let's go at it. Because the inductor acts like a perfect wire, what's the current flowing through the inductor? Yeah, hopefully you see it. We can essentially ignore that inductor. And so what we can do is apply, probably KVL is the easiest way to go. Let's just apply KVL. Okay. And if I'm going to walk counterclockwise around this loop, what we end up having is two potential drops across the resistors and two potential jumps across the batteries, or the voltage supplies, I should say. 2 equals. Now I'll go ahead and use an uppercase I, because we're talking about when these things are fully charged, so the currents won't be varying at all. And then we have R1 plus R2. So what we can write is that, I'll label it like this, the initial current flowing through the inductor is given by the sum of the two potentials divided by R1 and R2. So that's one of the needed equations, needed initial conditions. Cool. Well, let's say if this is the current flowing through that initial circuit, now we need to think about where we can get a second initial condition. And so I will think about for a moment the potential drop across the capacitor, right? And so the capacitor, let me get rid of that. The capacitor is located right here. Let me do that in some sort of other color. Capacitor is located right here in the circuit. And so if we're thinking about grounding, let's go ahead and ground that bottom branch. And then that allows us to get an expression for the initial potential difference across the capacitor. Go ahead, take a minute. You see it? Yeah. So you have this jump of V2 over the right potential supply. You can ignore the wire, and then you get this drop across R2. So what we can write is that the initial potential difference across the capacitor, and you could do that with the V1 as well if you wanted. I'm going to write this as V2 minus R2 times I naught. So what we get at the end of the day, if I get a common denominator, we have V2 over R1 plus R2 minus R2 times V1 plus V2, all divided by R1 plus R2. And Greg said a common denominator, and he only wrote the denominator portion. So there we go. Okay. Now we see that we get a bit of cancellation here. Right, V1 times R2 minus V2 times R2. So that one cancels that one. Right. And so what do we have at the end of the day? We have R1 times V2 minus R2 V1, all divided by R1 plus R2. Good? Okay, good. Yeah, for a moment, this looks kind of goofy, this equation. It doesn't look like the voltage divider equation. And I had to think about it for a moment. It's because I grounded the lower branch. If I grounded this branch on the corner, then I think we'd have something that looks a little bit more familiar. Okay, so we have now our two expressions for the initial conditions. And please bear in mind, we have all of those numbers on the figure itself. So I called this one V1, calling this one V2. I'll put R1, R2, and R3. And I'll just call this L and C since those are the only two there. Okay. So we're done with that piece. Okay, we have now finally solved our circuit for just the initial conditions. Now we have to actually figure out how to solve this thing for the time varying behavior. We have to flip the switch, and so let's go ahead and consider that. So I've taken the liberty of redrawing the figure, or well, recopying it, I guess. And so now we're off and running to the races. Once the switch is flipped, we can completely ignore this section of the circuit. It has now been officially removed. Okay, so we don't need to worry about that anymore. And so now we are dealing with this right part of the circuit. Now, one of the issues that I've failed to emphasize in my previous videos, please remember that at this point, you can analyze this circuit by whatever technique you find the most convenient. Okay? So, for example, you could do something like equivalent resistance. I have two resistors in parallel within the circuit. They are connected between the same two nodes, right here and here. And so I could combine those into an equivalent resistance and then just treat my RLC circuit from the last lecture. We did an RLC series circuit already. So you could take the results of that and just simply apply your initial conditions. Well, you say, oh, I don't like that, Greg. Let me do something else. Let me do node voltage. That's also perfectly acceptable. We'll have to ground that node and then treat both of these nodes, say A and B. And you'll get two equations that you have to finagle a little bit. Still better than running Kirchhoff's laws. Or say you don't like that, you want to run a mesh current. And so you do two mesh currents around these two loops. Those are all perfectly legitimate methods and approaches. Okay? Some will be easier than others. Okay? Source transformations is another one. You're perfectly fine to do source transformations. Okay? Bear in mind, the only thing that you should keep in mind is that you're going to be dealing with time varying currents and time varying potentials, not constant currents and constant potentials. Okay. So the math might get a little bit more particular. We'll call it particular. So, yeah, I don't know. You can pick your favorite thing to do. I will go ahead, just to give us a different type of example, I'm going to go ahead and apply node voltage. So I'll call that node A. I'll call this one node B. Okay. Just to give us some different flavor for what we're doing here. Okay. So if I'm talking about node A, convention is that current is flowing away from node A. And from the previous figure, I went ahead and grounded that, the bottom branch here. So I'll just keep doing that. Notice that that bottom branch is not necessarily an essential node anymore. It's probably not even the best pick for this problem, but I'm going to do that because this is the potential difference I'm actually interested in, the drop across the capacitor. So for node A, let's go through. We have something like the difference between the potential at A times the potential at B, minus the potential at B. And then we have the resistors in the path. I'll call it R2 and R3. So I'm combining two of those. And now here's the next point. Okay, I'll highlight this for node voltage, but you have the same issue for mesh current. Okay. Remember that the underlying physical idea for the node voltage method was applying KCL. Right? You're thinking about the currents exiting that essential node, and then you write those currents in terms of potentials using I'll say Ohm's law. Right? That's exactly how we got this expression. We took V, we divided by R. So we're thinking current through the resistor. That current can be expressed via Ohm's law as V over R. Now, if you're okay with that, hopefully you're okay with the next step. Remember that, okay, this node voltage method is based off of thinking of currents. So I should have in here as well a current going into the capacitor, the top plate of the capacitor. And I'll set this whole thing equal to 0. And now we ask ourselves, okay, for the resistors, we use Ohm's law to take the current and express it in terms of potentials. We should now go ahead and look at the relationship between potentials and currents for the capacitor. And with that relationship, eliminate I. Take the current flowing through the capacitor and express it as a potential across the capacitor, just like we did for the resistors. So we have to go to our equations. And we have to think, okay, well, what is Ohm's law for the capacitor? And that equation, relating the potential across the capacitor, is not for current, but for charge. And so here's where we start getting our differential equation. I don't want the charge on the capacitor, I want the current. And so with this bottom expression, I'm going to take a time derivative. If I take a time derivative, and now I'll tailor it to our selection, this would be a time derivative of the potential at node A, dt. Now I have a way of expressing the current at C, at the capacitor. And so what I'm going to do is take this expression, now relating the current flowing through a capacitor to the potential drop across the capacitor, and I should be more specific, the time dependence, or excuse me, the derivative of the potential drop, okay, the changing potential. And I'm going to substitute it right up here into my original equation. That's what's going to go right there. Okay? So that's how the node voltage method starts producing differential equations. It's when you consider the capacitor, you have to take a derivative to get the current. Just like we'll see for node B, we're going to have to do something as well. Cool, huh? It should come out the same way, right? Don't forget, these are based off of KCL and KVL. So let's go ahead and do that substitution. I will go ahead and I guess we'll get rid of this. Okay. So rewriting this, we have, get rid of that, C, the capacitance, times dVA dt. So there's one of our node voltage equations. Well, let's go to B. We have to consider B, and we'll do our same song and dance. That first term doesn't change at all. Well, of course, we have to switch the directions, just like we've practiced. And now we have an issue with the inductor right over here. Go ahead. See if you can hack out an equation. You got it? Sweet. Okay, so now we have to remind ourselves, what's the relationship between currents and potentials for an inductor? And we start scratching around and we realize, okay, the potential drop across the inductor, excuse me, frog in my throat, is given by the inductance times di dt. Right? Rather than it being the charge, as it is for the capacitor, here it's related to the changing current. Okay? Now we have to be careful when we're tailoring to our specific situation here. We have to think about, how do I include the potential source, that supply, in this equation? Okay. Don't forget, I said the potential drop across the inductor. So for this specific situation, what we'll have is VB minus what I called V2. That's what I called V2 over here. That's how we're going to incorporate that potential drop. And because I'm interested in having the current across or through the inductor, I will have to rearrange this equation to move the derivative to the other side. Right? Move the derivative, get rid of the derivative, if you will. So I have got my expression for, go 1 over L. I have now got my expression for the current flowing through my inductor. And we're done. Well, no, not quite. We're gonna have to finagle here. So we're gonna have to figure out, how do I get these two equations and combine them? Unfortunately, as I hinted before, we can't use our matrix methods. This is a nonlinear equation. So we're gonna have to finagle. Well, the first thing I would recommend doing, and especially for this second equation, okay, so let me get rid of this for space purposes. For the second equation, I would get rid of the integral. Okay? That'll just make life easier. Or you could get rid of the derivative in the first one. This bottom equation is sometimes referred to as an integral equation. Integral equations are a lot more difficult to deal with. So let's get rid of the integral. So for the second equation, what I'm going to do is take a time derivative of the entire thing. And here I'm also going to introduce a new notation. So because physicists and mathematicians are lazy, okay, because we are lazy, physicists in particular use a different notation for time derivatives. Okay? When we have a time derivative, we get tired of writing d dt all over the place. Say I'm using x as my variable. More often, you will see this dx dt written simply as x dot. You've kind of seen this in math. If you have dy dt, sometimes dy dx. Sometimes you'll see this just simply written as y prime. Physicists, engineers, we have actually two different types of derivatives we have to do. We have time derivatives and we have spatial derivatives. And so we use both of those. That's why we have this dot notation. When you see dot notation, convention is it's a time derivative. Whereas if you see prime notation, that's a spatial derivative. I'm going to start adopting this just simply because I am lazy. I don't want to have to keep writing dTs all over the place. So I'm going to take a time derivative of the second equation. And you can see this first equation, I can, instead of writing that ddt, I'm just going to write VA dot. The second equation, I'll take a time derivative. Well, that would give me VB dot minus VA dot. So close those. One over L. And now, because I'm taking a time derivative, right? I'm taking a time derivative, that gets rid of this integral altogether. Pretty cool, huh? Maybe. Okay. So you see there's some finagling in our future. Okay. We have two equations here and here that we can now use to get, say, for example, one of the time varying potentials by itself, VA or VB. Of course, once we have one, we can do the other one. Ready for it? So I think the process I am going to do is that I am going to use the node A equation to get the potential VB by itself. So I'll use the node A equation to get VB in terms of VA. And then I'll substitute it into the node B equation. And then I'll have the differential equation I need. Okay, ready for it? Okay, here we go. Go ahead, get VB by itself. Yeah, you got it. So what we end up having is, I'll go ahead and rewrite this common denominator. What we end up having is VA times R1 plus R2 over R1 times R2 plus CV dot A equals VB times R1 plus R2 over R1, R2. Okay. And then you can go ahead and, excuse me. Of course, you caught that already. It's R2 and R3. Yeah, I know I only had to erase half of those. I like having them in increasing order. Personal preference. Okay, so now we're done, right? We have VB is equal to VA, and then we have plus C R2 R3 over R2 plus R3. And I'll put VA dot. And now you see, okay, well, as expected, our node voltage technique is giving us the equivalent resistance, right? That REQ. And in fact, I'll just call it the equivalent resistance final. I'll just call that whole thing rigmarole. Now, the issue is, if we go back and look at our second equation for node B, not only do we have VB, but we also have time derivatives of VB. Well, okay. That means that we need to take a time derivative of this equation as well. And here's where the dot notation is helpful. Just allows you to write it really quickly. VA dot plus, I'll put this as REQ now, REQ final. Because don't forget, when you do the initial case, you could argue there's an equivalent resistance there as well. So I'll call it REQ final C VA double dot. Well, now we're at a situation where we'll have to take these two expressions and substitute them into the node B equation. Okay. It's going to be a little bit longer. We should be able to combine stuff. So what we now can do is substitute those in. And keep in mind, this expression that I have underlined here is just 1 over REQ final. So what do we have? Well, let's substitute in everything. And we see that we have something like VA, well, I shouldn't say something like, we have plus REQ final times C VA double dot minus VA dot. So that's just that first factor. The second factor is 1 over REQ final. And then added to it, we have plus 1 over L. And now we take our original expression for VB. So what do we have here? We have VA plus, and again, I'll leave this as REQ final times C times V dot A. So that's just for the VB term. And then we have minus V, and I should say V2. And that whole rigmarole equals 0. Well, looking at that first term, I know it looks imposing. Okay? You have, hopefully, again, it's not the final equation that you should be looking at. Think about all the steps that we took to get to the final equation. Okay? And if you trust each of those steps that we've gone through and you're confident in our application of those, then this is the equation that falls out, regardless of how ugly it is. What's important is that you understand how that equation was built. Now look at this. Let's make it simpler. I have a VA dot minus a VA dot. So those two terms cancel. And furthermore, I have an REQ final divided by an REQ final. Well, that's spiffy. So let's go ahead and get rid of that. So we can cancel that with this. And so what we end up with at the end of the day is a C V A double dot. Okay. And now we have some other stuff here. So we have plus, I'll go ahead and put it in order of differential terms. So I've got my double dot term. The next one I'm going to write is my single dot term. So what I have here is REQ final times my capacitance divided by my inductance, VA dot. Then I have my plus 1 over L VA, and then I have this minus V2 over L equals 0. And there is the differential equation that I now need to solve. Oh, this is why it's important or helpful to choose the right technique. When you choose the right technique, you can make this go really fast. Okay? I shouldn't say really fast, but faster. And it depends on the problem again. Okay, well, let's go at it. So we have a couple ways of actually tackling this sucker. I'm going to go through and divide by C, the capacitance. Okay, so you ready to go? Yeah, okay. Now we have a couple of different ways that we can go at this. Okay. One way would simply be to take another time derivative. You notice that we have an inhomogeneous equation. Inhomogeneous equation. The upshot is that it is a constant. So one way to get rid of this sucker would simply be to take another time derivative. And then that will set this to 0, and we'll have our homogeneous case. That's one way to do it. The other way to do it is to realize that since this is a constant, when we get our VA, our expression for VA in terms of time, right, we just simply have to have that constant added in. Right? If I have my VA as a function of time, imagine that you just add in that V2 over LC here. Okay? Then when you take a derivative, say this is VA as a function of time, when you take that first derivative, that second term disappears, goes away. Okay? So okay, so let's go ahead. I don't know, pick your pleasure. Let's go ahead and just solve for VA, and then at the end of the day, we'll tack on this V2 over LC to correct for this piece that we've ignored. Okay. So yeah, let's do that. Now notice, first of all, that in your B position, the first derivative position, we now have that tau, that time constant that we saw when considering the RL circuit. That is defined as tau. 1 over tau, excuse me. I always get those mixed up. It's 1 over tau. Now, right here, this 1 over LC, that is sometimes called the natural frequency of the circuit. Okay, that whatever, right here. So that's usually called the natural frequency, and oftentimes you'll see it given the value omega naught squared. Or if you prefer, you could do the square root here. Okay, well, we apply our characteristic equation. And so you know that you'll end up with something like, I'll use lowercase r squared plus, you could express this as 1 over tau if you want. I'll leave it as REQ final over L times R plus 1 over LC. Excuse me, this is, plus 1 over LC equals 0. And we go ahead and apply our quadratic formula. So this step is rather boring, actually, right? I mean, you're just applying your quadratic formula. 1 over REQ final over 2L plus or minus, okay, and I'll take that 1/2 and move it inside the square root. So what you end up with is 1 REQ final over 2L squared minus 1 over LC to the 1/2. Good so far? Okay. Now, I'll stop here and again highlight that the behavior of the value of this term, the square root term, will determine the behavior of the circuit. And by behavior, what I mean is it overdamped, underdamped, or critically damped? So it's right there that you can do your comparison. Once you have this expression, you can ask yourself, overdamped, underdamped, or critically damped? And you'll have to sub in the values there to determine that. But if you know which one it is, then you have an idea about the rough form of the solution. Let's go ahead and figure out which of these three situations we are actually dealing with. So we said REQ final. Remember, REQ final is R1, R2 over I did it again, R2, R3. R2 plus R3. That's our REQ final. Then we have a 1 over 2 times L squared. And we're interested to know how that compares to 1 over LC. Yes. Okay. Sehr gut, sehr gut. So for our particular problem at hand, so now we actually have to look at our values, 480, 960. So we have 480 times 960 over, let's see, 480 plus, so that gives us 1040, 1440. Should have known that. That's like high def monitor resolutions, right? The aspect ratios. Over 2. Let's go ahead and take a look at this. The inductor is 0.5 millihenry. So it's almost like they were planning on us looking at stuff at some point. There's 0.5, and then the milli would be 10 to the negative third. So there is the right side of the equation. And we want to know, how does that compare to our 0.5 millihenry? And we better get the capacitor, 12.5 nanofarads. So you can see these things are really small. Right, 12.5 times 10 to the negative 9th. Okay. Well, let's go ahead. We can ballpark this, I believe. So over here, 10 to the negative third, 10 to the negative 9th. So we get something like 10 to the 12th in the numerator. And in the denominator, half of 12.5. That's 6.25. How about over here? Let's cancel some zeros, I guess. So the nice thing is the 2 and the 5, 2 and the 0.5, those equal 1. We can get rid of that sucker, or get rid of a 0 on all of these. So what do we have? I'm sure there's a common factor, 12. There's a common factor of 12. 144 is 12 times 12. And so I have a set of 12 here. So let's go ahead. Let me go to a different color so you can see what I'm doing. So this, if I divide that by 12, I get 4. If I divide this by 12, I get 12. And 96 divided by 12 is 8. So I can cancel this one and get 8. And that takes care of this 12 in the denominator. So at the end of the day, I get something like 32 times 10 to the third quantity squared. So something like 32 squared times 10 to the sixth. And I'll put a question mark here. So what situation are we dealing with? Yeah, we have an underdamped situation, right? You don't even have to bother doing that. I mean, this at most will give you another 10 to the third, right? 30 squared is 900. So let's round it up to 10 to the third. So you have something like 10 to the ninth on the left-hand side and something like 10 to the 11th on the right-hand side. This is an underdamped situation. So what are we dealing with here? We have an expression for v of a, and now we can write it out. I'll put it's some constant a cosine of omega d times t plus b sine of omega d times t. Okay. And I think we went through and we showed that, right? We put in the r plus, the r minus. We pull out the imaginary terms, combine those using Euler's relation to get these cosines and sines. Okay. Then that whole rigmarole, that takes care of the cosines and sines. This would still be multiplied by e to the negative r, final equivalent resistance divided by L times time. And then we had that V2 over LC tacked on to the end. And you can see when I take a time derivative, that piece goes away. Well, let's go ahead then. We now have an expression for, if you remember, the potential drop across the capacitor. That is the potential at node A, as in apple. Okay. The last thing that we need to do is figure out what the values of our coefficients are based on the initial conditions. So you thought you were done. Oh, nay, nay. Still have to keep going. We're fortunate, though, that we have those. Way back, you remember way back when at the start of this sucker. I know. Okay. So we have these values. Okay. Let's go ahead and apply this one, the potential drop across the capacitor initially. That's going to be the easier of the two to figure out, or to apply, I guess I should say. R1V2, R2V1. Okay. So we go all the way over here, and we know that, so let's apply that. VA at time equals 0 equals V. 2R1 minus R2V1 all divided by R1 plus R2. Okay. That's the initial condition. So we're trying to match the time before, time less than 0 state with the time greater than 0 state. That's what this is. Okay. And so they have to match. In other words, the function has to be continuous at time equals 0. That's essentially what we're doing here, making sure that our function time less than 0 is continuous with our function with time greater than 0. And so what do we get? Well, we can substitute in 0 for all of the times that we see, which makes it nice, easier. We have something that says, okay, well, this would be A. Cosine of 0 is 1. We get 1. Plus B. Sine of 0 is 0. We have e to the 0, which of course is 1. And then we have plus v2 over LC. Well, sweet. This gives me the value of A. Right? You see it? Right? All of this is known. All of this is also known. And so what we end up with, if you'll forgive me, I will just, instead of rewriting this, I'll call this the initial charge of the capacitor. I'll just write it like that for right now. Or initial excuse me, I keep saying charge. The initial potential across the capacitor. And so we get something that says the initial charge, or the initial potential across the capacitor minus this V2 over LC value. That whole rigmarole is equal to our coefficient A. So that's how we can apply these initial conditions. So there's one. Okay, check. We've got A. Now we have to figure out how to use our second initial condition. And that becomes a bit difficult because the initial condition wasn't being applied for the capacitor. It was related to the inductor. Okay? So this is where it gets a bit finagly. Okay? The issue is that we want to apply an initial condition that was derived for another circuit element to the capacitor. Okay? And so we're going to have to do some finagling. The other issue is bear in mind that we have to set not only some sort of restriction on the value of the function, VA, but we also have to set some sort of restriction on how VA is changing. Okay, so let's go at it. We have an initial condition dealing with the current in the inductor. Okay. So let's go ahead and think about our circuit, our final circuit, and the initial condition on the inductor. Okay, so I have taken the liberty of rewriting the current, the initial current going through the inductor, the minute that the switch is closed, or switch is changed, maybe I should say. Okay. And now the question is, we're trying to figure out how to relate this back to the capacitor. So let's go ahead and think about for a minute again. We know that the potential across the capacitor, node A if you prefer, is related, and I'll use the dot, to the capacitor current divided by the capacitance. Okay. Remember, we're taking our general equation for the potential drop across the capacitor, and we're just taking a time derivative. Okay? Good. Now, here's how we apply our initial condition. Remember that right here, we have a current flowing through L, and it's actually going, if I recall correctly, is it going left to right or right to left? It is going from right to left. Okay. That's the direction of the initial current flowing through L. And keep in mind is that at time equals 0, when that switch is flipped, L, the inductor, wants to keep the current flowing the same way that it has been. For a brief instant after the switch is closed, L, the inductor, keeps the same current going in that direction. For this case, what does that mean about the current flowing through the capacitor for a brief instant after the switch is closed? So for this case, the current flowing through the capacitor right at that brief moment in time, yeah, you see it? We could set it equal to this sucker. We get VA, the time derivative of the potential, is equal to, and now I'll replace it with this capital I, naught over C, and this is at time equals 0. Okay. Any instant after that, this equation no longer applies. This I, rather than being capitalized, will be lowercase. So what we have to do to apply the second initial condition is to consider the time derivative at A at 0, and then set that equal to this IL naught. So let's go ahead and do that. We have our expression for VA. Okay. So VA equals, I'll write it down again just so that we have it here. So bear with me. And don't forget, we already know what the value of A is. We've checked that. We've used the initial condition on the capacitor to find VA. So we need to find VB. First off, take a time derivative. Okay, so now we're at a position. Let's go ahead and take a time derivative. Ugh, right, product rule. Okay, well, this is going to get messy really fast. We give A omega d sine of omega d t, and there's a negative sign there, right? And then you have this e to the yada, yada, yada floating out front. We have this b omega d cosine of omega dt. Not for the faint of heart, is it? We have this e to the negative req final over L times time. And then we have to take the derivative of the second piece. So we have a negative req. Fortunately, the derivative is easy to do. E to the negative req over LT times this a cosine of omega dt plus b sine of omega dt. The upshot being that last term wipes out. We don't need it anymore. Now we have to evaluate this at 0. This will simplify to a smaller extent, right? These e's become 1. The signs disappear. And what we end up with is that b omega d cosines equal 1. So that's this term. And then we have minus req over L times A better darn well be equal to IL naught over C. Now, of course, you usually have numbers, right? These are all numbers, but we're done. We know the value of A, so we can now find what the value of B would be in order to match all of the initial conditions. Right? B is equal to some number, the initial current flowing through the inductor, divided by the capacitance, plus the final equivalent resistance divided by the inductance times whatever A is. And remember, we had A right here. And here's B. So it seems like we should probably have a summary page. Let me go ahead and put everything together as a summary. So, summary, I know it's a long process, so I'll just walk you through a couple of these. So we started off with the initial condition, and that allowed us to find the current running through the inductor and the potential drop across the capacitor. After that, we went through and we applied node voltage. That was chosen just to try a different technique. And through node voltage, we arrived at a second order differential equation. From that second order differential equation, we can form our characteristic equation, which I have written here. After that, we look at the coefficients to the linear term, the coefficients to the constant term. I guess coefficient's the wrong word. And we compare those two. And from that, we can determine the behavior of the circuit. For the case that we are dealing with, we found that it was underdamped. That means that our solution will be of the form cosine sines with an exponential decay. And I've tacked on the end here because of the form of our second order differential equation. We had an inhomogeneous equation, but it was a constant. So I can just tack that on the end here. Okay. Now, of course, I've changed some of the notation only because I'm lazy. And so please bear in mind that omega d is given by this expression. Notice I flipped the order to make sure that we end up with a non-imaginary number. The imaginary portion is taken care of with the sines and the cosines. Okay. And lastly, we took these initial conditions that we found, and we used those to find expressions for both A and B. Okay. So I know that's a long process. Okay. And so I think at this point, we'll call it quits for this video, but I've got a couple more that will have some additional examples. Hey, thanks for your attention. I'll see you next time.